Hi, welcome everybody. Thank you for coming up to our bi-weekly seminar. Okay, today it's my pleasure to introduce Dr. Shu Lu from University of North Carolina, where she's an assistant professor in the OR and Stat department. She got her BS and MS degrees in civil engineering from Tsinghua University and got an MS degree in mathematics and industrial engineering from University of Wisconsin, where she also got her PhD in industrial engineering in 2007. She's currently an assistant professor, as I said, at UNC, Stat OR department, and her research interests are in the area of optimization and variational inequalities and variational analysis. It's a pleasure to have her here. Thank you for coming.
Thank you, Hamid. Thank you for inviting me here. It's a very good opportunity for me to hear, to get to know what you are doing and to also introduce you to what I'm doing. So today I'm going to talk about, give you perhaps a brief introduction to our type of problem. It's called finite-dimensional variational inequalities. And I will go over some typical applications of this problem. And I will briefly talk about the main ideas in the algorithms to solve this problem. And then I will talk more about the solution properties that we know about these problems. So here is the outline of the topics. I will start with definitions of the problem, and then talk about example problems, and then algorithms and solution analysis. So perhaps many of you have some knowledge about optimization problems, but less knowledge about variational inequalities. So let me start with, let's start with an optimization problem. Suppose that you are minimizing the function capital F, which is a function from the n-dimensional space to the real space. You minimize F over our set capital S, which is the set of all feasible solutions, and which is a subset of Rn. And then this is our so-called constraint optimization problem, because you have the set capital S representing all the constraints. Now, it's well known that if the small vector denoted by small x is a local minimizer of this optimization problem, then it must satisfy two conditions. First, itself must be belong to S. That's obvious. And the second is that if you take the inner product between the gradients of capital F evaluated at x with any tangent vector v, then that inner product has to be greater than or equal to 0.
You don't understand how that can work.
Of course, here we assume that the function capital F is differentiable at x. Now, this is sometimes called the first order necessary condition of optimization problems. And what this says is that if you start from the vector x, and then you move along a direction v, the tangent direction, then since x is a local minimizer, then you should note the function value of capital F should only be increasing. Inner product is non-negative. Now here I use this notation, Ts of x. That's the set of all the tangent vectors to the set capital S at the point X. And I'm not going to, here I've also included the formal definition for the tangent cone. It's the limits of all the, it's the set of all limits of the quotients of the form that you have xi, the difference between xi and x over some positive scalars, lambda I. Now, then, if you further assume that the set capital S is convex, then indeed any tangent vector can be just put in the form of our difference between x prime and x for x prime in S, so that you can rewrite the equation 2 over there into equation 3. So that instead of requiring the inner product between the gradient of f and any tangent vector v to be non-negative, you just direct the inner product between the gradient of f and the difference between x prime and x to be non-negative for all x prime in S. And that's the equation 3 here is already a variational inequality. So in other words, for a variational inequality, we look for x in the set capital S such that this inequality holds for any other x prime in S. Now here is a more general definition of variational inequalities. That's given in equation 4 here. In this talk, we restrict ourselves to only convex sets, capital S. Now, if you are given such a set S, and you are also given a function denoted by small f here, from S to Rn, we call that S is a subset of Rn. So f is indeed a function from Rn to Rn. Now, if you are given a set S and a function f, then the variational inequality problem is to try to look for a point x in the set S such that the inner product between f of x, which is our n-dimensional vector, and the difference between x prime and x, which is another n-dimensional vector, to be non-negative for all the points x prime in S. Now, we can further rephrase this equation if we introduce the definition of normal cone. Now, if you have a point x in the set solution to the set S. And that's the general definition of variation. In other words, the loop point in the set S such that the function f valued at that point is a normal vector to the set S at that point.
I'm not new, I don't know the system. It worked when I was over here earlier in the last week, but I don't know what went on. I can't reach nobody.
To some more special form. For example, if the set capital S is just the whole space Rn, then the normal point to Rn at the point is just the origin. Then this variational inequality will reduce to an equation that says 0 equal to f of x. Now, for another special case, let's consider the set S to be the non-negative ordinate of Rn plus. Then in that case, if you have a point x that belongs to S, then the normal cone there would be all the non-positive vectors that are perpendicular to x. And then, using this expression, you can rewrite the variational inequality so that it becomes such a requirement. Here, it said that the solution must satisfy these conditions. First, itself has to be non-negative. This is for it to belong to S. And then f of x have to be non-negative as well. All of the components of x has to be non-negative. And they have to be perpendicular to each other, meaning that their inner product has to be 0. And such a problem is called complementarity problem. Now let's look at two examples. The first one is a traffic user equilibrium problem. And here is an example in which this is a transportation network for the city called Shu Lu, but it's of course simplified from real. And in this network there are 24 nodes and 76 arcs connecting pairs of nodes. And for transportation problem, we consider travelers who travel from their origins to their destinations. And you can pair the nodes up. And here we consider a total of 528 pairs of origin destinations. And you will know the travel demand between each pair of origin and destinations. And the problem is to decide which roads will these travelers take, so that you can then decide how many travelers will travel along each link, each arc. The weights on here those weights are just numbers of the arcs. For example, I think here this means 76. This is just the number of arcs. Right. Arcs. Well, by arc I mean links or edges. So there are 76 arcs. You can see the number. Well, we can consider. Indeed we will consider the capacity and also both the capacity and the length of the arcs. But I didn't include those data in the network problem. Here, those numbers are just the number, just the numbering. It starts from 1 somewhere. Here, that's arc 1, and then I have arc 76. I didn't write down the length or the capacity here in the network. The problem, well, you know that, so there are 528 pairs of origin destinations. For example, one pair would be from node 1 to node 2. And you know how many people will travel from node 1 to node 2, for example. And you want to know which path they will take. Of course, yeah. Yeah. So for example, of course, I mean, from 1 to 2, there are not that many paths. There are not that many alternative paths. But if you consider a pair from 1 to, say, 20, then there are a lot of different options. So you want to know how many of them will travel along this path and how many will travel along this path. Sometimes there will, be portions of travelers who travel along different paths. Okay, all right. Now, this is an equilibrium problem. So here, for this specific problem, there's not a single objective. Then let me go to the second slide. Here, it's like a decentralized problem, so that the travelers, they try to minimize their individual costs or individual travel time of reaching their destinations. So each traveler wants to minimize his or her own travel time. Travel time or cost is the equivalent. So we are not trying to minimize the overall travel time, for example. But those two different problems, they can be equivalent in some senses. I'm not going to details about that. Now, of course, this might be simple if the travel time are not changing. If you just consider each link to have a constant travel time, then it's easy. You just take the shortest path for each OD pair and let all the travelers to travel along the shortest path. But the problem here that makes it more complicated is that, should I do anything? All right. So what complicates this problem is that we consider the travel time or the cost to depend on the traffic volumes. So that in the sense that when there is traffic congestion, then the cost will increase, will get higher. So then that's how this equilibrium is captured. That's the basic principle behind this equilibrium problem is that for each origin destination pair, only the roads that have the lowest cost can have positive flows. So for example, if between the node 1 and node 20, there are, say, 100 different routes, and then if two of these out of these 100 roads have the minimum cost, then only those 2 roads may be used by the travelers, and the other 98 roads will not be used at all. And that's the basic principle. And then if you write down that principle mathematically, you get such a problem, which is indeed our complementarity problem. It's a mixed complementarity problem. Here, let's start with this notation. dW is the demand between the OD pair W, and then QP is the flow on road P. So that the second equation here just says that for any pair of origin, that's, for any OD pair, the sum of the road flows for those roads between this pair has to be equal to the demand. So the demand is exactly satisfied. And then the first equation here says that this first equation just reflects this principle that only the lowest, the roads that with the lowest cost will be used. The Cp of Q means the cost on road P. And this is the minimum among all the roads between pair W. So that if this difference is 0, that means road P has the minimum cost among all roads between pair W, then the flow QP can be positive. But if this difference is positive, that means road P is not the lowest road, then QP has to be 0 by this perpendicular condition. So this turns out to be our complementarity problem, which is, as we have seen, a special case of the of the variational inequality problem. And that's one example of the variational inequality problems. The second one is a well-known problem. That's the Nash equilibrium. We can consider n players, and each of these players needs to select a strategy to minimize his or her own cost. And suppose that for the player I, the set of strategies he can choose is denoted by key of I. That's a fixed given set. And also suppose that the cost of each player I, is given by this function, theta I, which depends on the vector x. Well, the vector x capture is all the players of strategies. So x1, for example, is the strategy of player 1, and xn is the strategy of player n. So it groups all the players' strategy into one single vector, and this vector x will affect the cost of each player. And then, if the other players' strategies are already known, so if x1 up to xn, except xi itself is known, then the player I will try to select his strategy xi from the set key I to minimize its cost. Now, this minimization problem, as we already seen, can be captured into this variational inequality here, meaning that the gradient of this cost function with respect to xi has to be related to this normal cone. Now, if you write down all of such variational inequality, one for each player, then you get this overall problem, which is a big variational inequality. So that's another example of the variational inequality problems. And you can see that both examples, they capture a certain types of equilibrium status. So that in general, we can say that the variational inequality is used to model various equilibrium problems. Now, how do we solve such problems? Well, we use iterations. And a common framework here is that you choose a starting point x0, and then at each iteration, you solve some approximating problem. You try to approximate the function small f of x by some linear function depending on your current iteration xk. So if you, so here this a of xk is just a matrix that depends on xk, if you just choose A of xk to be the Jacobian matrix of the function f at xk, then that's what the Newton method is. When at each iteration, you replace the possibly nonlinear function f by its linearization at the current iteration. Of course, if somehow it's hard to get the exact Jacobian matrix, then you can perhaps try to get some approximation that makes it a quasi-Newton method. And then if you just disregard any information from the Jacobian matrix, just use our fixed matrix capital G, then that will lead to a type of method called projection method. So, and such iteration will usually give you quite good local convergence results. But so that if you are already quite close to the solution, then it will converge pretty fast to the solution. But to get global convergence, you usually need to use some merit function so that you don't really use the solution from this approximating problem. Instead, after you find the solution, you may not just take that solution. Instead, you connect that solution with your current iteration xk to get a line segment, and then you try to do some line search along that line segment to find perhaps an intermediate point that give you enough decrease of the merit function. That is usually used to get global convergence, so that you can start from a point that's far away from the solution and still converge to the solution. And that's one type of method. And people also developed different types of methods based on the so-called KKT conditions. And we can write down the KKT condition if the set capital S is not just given to you as our arbitrary set S, but it's defined by finitely many constraints given by this function gi's. If this is defined in this way, then you can rewrite the variational inequality into its KKT conditions by taking the derivatives, taking the gradients of these constraints and introduce multipliers lambdas, and then relate the function f with these linear combinations of the gradients of the function of the gi's, and also there's some complementarity condition between the lambdas and the gi's. And this is a KKT condition, but you can see it's also itself our complementarity problem. So in other words, you perhaps by introducing the multipliers, you expand the problem from our variational inequality to a complementarity problem. So it has a simpler form, but has larger dimension. And then from here, you can devise various algorithms to solve it. For example, you can solve it using the interior point method, because the interior point method essentially it's developed from the KKT conditions. Well, for example, for linear program problem, you just write down the KKT condition of the linear program problem, and then try to solve the those conditions along, using some method similar to Newton's method, but you somehow modify it. And that's very similar to the way we develop interior point method for the KKT conditions of variational inequalities. So, so we have talked about the overall definitions of these problems, and the two example problems, and also the frameworks for algorithms. And now, let's give a closer look at the solution properties of these problems. And let's first study a very special type of problem, linear variational inequality. So here, equation 6 here is a variational inequality that has the function capital L here is a linear function. So it's a affine map from Rn to Rn. And the capital S is our polyhedral convex set, which means it's our set in Rn defined by finitely many linear constraints in this form. And then we also introduced our symbol W here, which will represent a parameter to this problem. And the basic question that we are interested in here is, under what conditions does this variational inequality have a unique solution for all W in Rn? So this is similar to the problem, like when does the linear equation Ax equal to B have a unique solution for all vectors B in Rn? So that's kind of a similar question. Of course, the problem here is more complicated. Now, the way we try to answer this kind of question is to reformulate this variational inequality into our function that we call the normal map. So suppose you given the set capital S and the function L it appeared here, and it was assumed to be a linear function. Then we can define a normal map denoted by LS, and which is going to be just a function from Rn to Rn. And it's defined in this way. And here, the pi s of z is just the Euclidean projection of z onto the set S. So you first take z, and you find its projection on S, and then you get this projection, and you evaluate L at that point, and then you add z minus the projection. Now, if you define the normal map this way, then the variational inequality over here can be reformulated in our equation like this. If you have if X is a solution to the variational inequality, then you can find Z using this expression, and then Z will turn out to be a solution of this function, which says that the normal map evaluated at Z is exactly equal to minus the negative of W. And also, X will be just the projection of Z. Now, what this means is that, let's take a look at this example. This is the set S, and X is this corner point. And suppose X satisfies the variational inequality, so that, and suppose W is just 0 here, then that X solves the variational inequality so that negative L of X will be in the normal cone. So that if you start from X and travel along that direction, negative L of X, you will get some point here, which we call Z. And then notice that if you project Z back onto S, you will get X exactly. And then if you evaluate the normal map at Z, you get L of x plus x minus z, which will be just 0. So in other words, the variational inequality is then reformulated as an equation that involves the normal map. Well, that's good news because we think that equations are easier to consider than the variational inequality itself. But the point here, the difficulty here is that the normal map defined in this way is not a smooth map because it involves this Euclidean projection onto the set S, which will not be a smooth function. But it does have some nice properties in the sense that the normal map is a piecewise affine map. Well, if you look at the set capital S here, and since it's a polyhedral convex set, it has finitely many faces. Now, what does face mean? Well, for a set S like this, then it has exactly 4 faces. One face is just itself, and then another face is this half line on this side, and then this bottom side is another face, and also the corner point X is the 4th face. So faces are like the intersections with between S and the half spaces that contain S. So now each face is in turn associated with a region in Rn, and on that region, the Euclidean projector coincides with our affine map. So for example, this side of S, it's associated with this region, or the region on the left. And you can see that within this region, the projection onto S is just the same as the projection onto this vertical axis. And the vertex X corresponds to this region, the lower left region, because from everywhere in this region, the projection is just X. And similarly, if you the face S itself, I mean the set S itself corresponds to the region that's just itself, because everywhere in this region, the projection is just given by the point itself, the identity map. Now, if you put all those regions together, you get a connection, and indeed, all of these regions are 4-dimensional sets in Rn, and that collection is what we call the normal manifold of S, and this has nothing to do with the smooth manifold, the differential manifold in other areas of mathematics. It's more like a piecewise linear manifold. Then if you call that collection the normal manifold in this way, then we can say that the normal map is a piecewise affine map on the normal manifold of S, because it coincides with our affine map on each region in this normal manifold. Now, then we can we also have this theorem that says this normal map is a Lipschitzian homeomorphism from Rn to Rn if and only if it's coherently oriented, which means that the determinants of all the affine maps representing this normal map have the same non-zero sign. Now what this means, well, if you look at this example, then the normal map here, it coincides with our affine map within S, and another map on this region, and another affine map in this region, and another in this region. So it's going to have, there will be 4 different affine maps that represent the normal map in 4 different regions. But if all of these 4 affine maps, they are representing, I mean, the matrices representing those affine maps, they are all non-singular, and they all have the same, their determinants all have the same sign, either all positive or negative, then that normal map will be a homeomorphism from Rn to Rn. Now, if you then use that relation between the normal maps and the variational inequality, then you will be able to conclude that this variational inequality has a unique Lipschitz continuous solution for each W, if and only if that coherent orientation condition holds. And that gives you a complete characterization of the solution when this variational inequality has a nicely behaved solution. It's when all of these matrices have the same non-zero sign. Now, we can further complicate this problem by introducing another parameter u. Remember that the set S over there, if you go back to the definition of the variational inequality at the beginning, and then there the set S was defined by, in this way, u was the right-hand side, but we have, so far we have treated u as a fixed vector, so that S is also a fixed set. But if you now allow u to change as well, so that we write S, the set S as a function of u, then we can consider this parametric variational inequality in which we have 2 parameters, both W and U. And then we can develop some similar results. This variational inequality has a unique Lipschitz continuous solution near some base points, if and only if some extended version of the coherent orientation condition holds. That part was about the solution analysis of a linear variational inequality, in which the function f was just a linear map, and the set S was just a polyhedral convex set defined by finite-dimensional linear constraints. Now, when you consider more general form, when the function f is some smooth function, and the set S is defined by those constraints GIs, which are not necessarily linear, but they will be smooth. And you can still introduce parameters into this problem by keeping u in the picture. Then the problem becomes much more complicated, not only because f is now nonlinear, but also because the set SU is defined by nonlinear constraints. And usually, for those nonlinear constraints to behave reasonably well, we need to introduce certain types of constraint qualifications. Well, to do that, we also need, usually we also need to talk about the active constraints. So if you have a pair XU, then usually we use capital I of XU to denote the set of active constraints. These are the constraints that are not only satisfied at X and U, but also satisfied as exact equations. Now, if you use that notation, then there are various constraint qualifications that you can talk about. There's LICQ, that's linear independence between the gradients of those active constraints. And there's MFCQ, that's more general. And there's also CRCQ that requires the gradients of the active constraints to be remain of the same of a constant rank for all nearby points. Now, what does those constraint qualification do? Well, first, they are called constraint qualification because they must first satisfy, because at least they need to result in the following expression of the tangent comb and the normal comb of the set S of U. And recall that the set S of U was defined by a bunch of nonlinear constraints given by the functions gi's. And the tangent comb, again, was the set of all the tangent vectors. Now, if any of these constraint qualifications are satisfied, then you can write the tangent comb there by just linearizing those constraints, replacing the function gi's by their gradients, and use the same directions, either less than or equal to 0 or equal to 0. Of course, these linearized constraints will give you a comb, a polyhedral comb, and that will be exactly the tangent comb. And now this equality here, it may not hold if you don't have a good constraint qualification satisfied. Now that's the main purpose for introducing constraint qualifications. And each of these constraint qualifications also have some other implications. For example, the LICQ will result in a local diffeomorphism between the nonlinear set and the tangent comb. And the MFCQ will imply some pseudo-Lipschitz continuity of the set's valued map S of U. And the CRCQ will allow you to define some curved phase structure for the nonlinear set S of U, and also some weakened version of the Lipschitz continuity. And then if you combine those constraint qualifications and with some maybe stronger versions of the coherent orientation condition, you can obtain results like that guarantee the existence, uniqueness, continuity, and certain types of directional differentiability of the solution of this parametric variational inequalities. And that's all I want to talk about today. Thank you for your time.
The solution set that you can get with these, in terms of implementation, what's the complexity of these problems exactly?
All right, the complexity. Usually I don't think there's very good complexity results for these type of problems. Usually you can get good local convergence, so that if you already know where the solution is probably then you start with very close by points, then the convergence result may be quadratic or linear or somewhere nearby in between. But for the global convergence, if you don't know where the solution is, and perhaps you just randomly pick a starting point and then go from there and use the merit functions to guide the line search, then I don't want to say for sure, but it's as far as I know, there's not much known that we don't know much about how fast it will get for the global convergence. We just know that if you follow this algorithm, it will converge to a solution, but we don't know how long it will take for the global convergence. But I think also it may also depend on the convexity of the problem. Now here, everything I talked about is when the set is, the S is convex set. But sometimes it also depends on the property of the function f. If the function f, has some monotonicity, strong monotonicity, then sometimes you can get a sharper result on how fast it will go and so on.